Hi folks, Mr. Long here. We're going to do a quick screencast on summation, which is also called sigma notation, and it's this notation right here. And actually, the whole integral symbol is changed, or is developed from that. Sigma just means total. So we did very briefly in grade 11. I think we spent a day on series. We had series and sequences, and series meant you added up all the terms. So what does this mean? Well, let's get some language out of the way. So it's called summation notation, but it's using the Greek capital sigma, which again is this weird shape here. And K, this K means, okay, what's the first number you're going to substitute into this sum? Okay, what's the first number you're going to substitute in? And they call that an index. So the name of this number here is called an index. And then the second number you'll sub in will be the next whole number. So the first number you sub in is 1, the second number you're going to sub in is 2, and so on. And then that's the last number you're going to sub in. So this is the first number you sub in, this is the last number you sub in, going up in increments of whole numbers. Okay, so then the formula we want to get the sum of is k plus 10. K equals 1, we're going to go with the formula k plus 10. So what I do is, this k here I then replace with, to start with 1. So the first thing in my series, okay, my summation is 1 plus 10. Then I change it to k equals 2. Okay, the index becomes 2. And then it's 2 plus 10. Finally, the last k value I'm using is k equals 3. And that is 3 plus 10. Okay, so this is k equals 1, k equals 2, and k equals 3. And then if we total all that up, it works out to 36. So this series or summation notation results in an answer of 36. So again, just a few things. K increases in increments of 1. And relating to calculus and Riemann sums, it's going to be, this number here is going to be, you're starting at rectangle 1, and this tells you the maximum number of rectangles. Okay, the maximum number of rectangles. So here's another one down here, 1b. And so for this one here, how are we going to figure out our answer? Well, we know the formula is, it should not be x squared. That's a typical Mr. Long error. That should be I squared. And by the way, so we can change this value here. I said that we call the index. It could be k, it can be, most typically k and I guess are the most common numbers used in it. So we're going to start with I equals 2, and we're going to square it. So the first thing we're going to do is replace, the first I value is 2. So I'm going to replace this I with 2. It's going to be 2 squared. Then we go up by 1. 3 squared. And the reason that's a plus is because we have this summation symbol. The summation symbol means we're going to add the term values together. Okay, then the next one would be plus 4 squared. And if we look at it, 4 is the last I value. Okay, add that all up. 4 plus 9 plus 16 is 29. Okay, that's how you go through that. Let's look at some more examples. You know what? So here's another example right here. And let's see. So this time, it's the same thing, except we change I to k. It's k squared. And we're going to start at 0. And we're going to go up by 1 until we get to 2. So again, what do? I replace, the first k is 0. That's a 0 square because there's k there. Then I have a 1 square. Okay, I'm adding on a 1 square. I change k from 0 to 1. It goes up by 1 each time. Then I add a 1 square. Then the last k value is 2. I add a 2 square. That gives you a total of 5. Okay, so here's how we do an integral. So this is a pretty simple integral to do, right? The area from 10 to 20. And the f of x, the y value all along here, is 40. So we know really easily this is going to be 40 tall by 10 wide. 400 is the area. But how would we do this with a formula? Okay, how would we do it with a formula? Like say we wanted to do it with 2 rectangles. Okay, 2 rectangles. So I'm going to have my k value as the rectangle number. So this is the first rectangle. That's the second rectangle. Okay, so k measures in this case the number of rectangles. So we're going to start at the first rectangle and we're going to go as far as the next rectangle. So think about the area of that. What is it? What is the area of that? Well, the rectangle is f at x tall and it's delta x wide. Okay, and now the area is the same for every rectangle. So the y value is 40 tall, the width is 5. So I did it for this case, k equals 1. So the first rectangle is 40 times 5, and the second rectangle is 40 times 5. Add all that together and we get 400. Okay, so now let's start to put things together in a little bit more complicated situations. So here's a straight line, y equals x plus 3, and that's f at x. And what we're going to do is we're going to create, or we're going to get the area under the curve between x equals 10 and x equals 20. And we're going to start writing some formulas here. Okay, writing some formulas. So, and we're going to do it with, let's say we do it with 2. Oh, by the way, the letter that we assign for the number of rectangles is called n. So n represents the number of rectangles. So in this one, say I wanted to have 2 rectangles. How wide would each rectangle be? That's delta x, right? How wide would each rectangle be? So the total width is 20 minus 10. So the total width equals b minus a. Okay, and the divided by the number of rectangles, n, will give me delta x, right? So 20 minus 10 is 10, divided by 2 rectangles is 5. Delta x is 5. Delta x is that width. Okay, so let's do the area with a right Riemann sum. I'm going to go through this process again with you. So we're going to do the area from 10 to 20 of f at x dx. As I said, we're doing 2 rectangles, n equals 2. So here's our formula to get delta x, b minus a over n. 20 minus 10 over 2 is 5. So that again is our delta x. Here's the hard thing. We have to figure out a formula for x. So if this is to be a right Riemann sum, that means I'm evaluating the height for the first rectangle, k equals 1, at 15. For the second rectangle, k equals 2, I'm getting the height at 20. So here's what we do. This is a pretty slick way of doing it. So by the way, with Riemann sums, you almost always do, with this type of Riemann sum, where you're developing formulas, you develop every formula as if it was a right interval. Okay, a right interval. And so we know the first rectangle, the x value was to be at 15, right? The x value was to be at 15. The second rectangle, the x value was to be at 20, okay, because that's the right side of that. See, it's the right side of that the rectangle. So what about if I had a k value of 0? That's just going to get us the y-intercept. Well, that's 5, so that would be 5, so it's 10. So what's a formula for the x value of the kth, we call that the kth rectangle. So the first rectangle, the x value is 15, where we got the y value. The second rectangle is 20th. So what's the formula for xk depending on k? Well, we know it's 10 plus 5k, right? 10 plus 5k. There's something really interesting about that. That's the letter A. This is the letter A, right? That's delta x times k. So A plus delta x times k. But what is that also? that also is a plus, and we know delta x is b minus a over n times k. So there's a formula for xk. All right, so once we get, now that we have a value for xk, we need to get a value for f at x, the height. We know in normal function notation that f at x would be x plus 3. What would f at xk be? So instead of having f at x, a continuous function, I'm going to get the height at the right side of every single rectangle. K equals 1 is the first rectangle. I should get the y value at the right side of it. Then I have to get the y value on the right side of the second rectangle, and so on. And we know that the formula is x. That's our x value. We figured that out, right? 10 plus 5k plus that extra 3 from the end of the function, x plus 3. If I simplify that, I get 13 plus 5k. Okay, so that's xk. So the last thing that we would do here is, and I'm going to go through a very specific process, a step-by-step process in a minute here. So then the integral of f at x dx from a to b is going to equal summation from k equals 1 to n, the number of rectangles, f at xk, and we know that xk is a plus b minus a over n multiplied by k, all multiplied by delta x, which is going to be from k equals 1 to n rectangles, because I can have different numbers of rectangles, f at a plus b minus a over n times by k, and let me just erase the end of this because we're going to overlap that, multiplied by delta x, and delta x is b minus a over n. Okay, so I'll just put these in different brackets so you can see them. Okay, so this right here is the height of each rectangle. This right here is the width of each rectangle. Okay, the height and the width of each rectangle. So, folks, what I want to do now is let's talk about, instead of having like how do we get the area under the curve to be more exact? Okay, how do we get it to be more exact? So let's take a look at this. So here's y equals x squared, and we're going to do the integral between 0 and 3. Okay, between 0 and 3, as you can see. Now, right away, you can see that it's a right-sided sum, right? It's a right-sided sum, and you can see that there's a huge overestimate, right? When a function is increasing with a right interval, you're always going to overestimate. What happens to how big, oh, we can see right here how big the overestimate is. So you can see on the right side, you see where that says 14? Okay, so that's the Riemann sum, that's the area of the 3 rectangles. The exact integral is 9. Okay, that's how big x squared is between 0 and 3. It has an area of 9. So you can see you're out by a total of 5 there. Now if we went back to just 2 rectangles, oh whoops, I changed the limits of integration. If I went back to 2, sorry folks, maybe it won't let me go to 2. Yeah, there's 2. So 16.87. You can see the area is getting bigger. Now what happens if I increase the number of rectangles? What do you notice about the area? And what do you notice about the error? Right? More rectangles means I'm getting closer and closer to those rectangles approximating the curve, right? And less area. So with 20 rectangles, the error is about 0.7. So 9.68 is the area of the rectangles, and the exact integral is 9. But again, remember, when I have less rectangles, there's more error, which totally makes sense. So you want to have n as big as it can possibly be. In fact, if you want to get the exact area, what do you need your number of rectangles to be to eliminate all area? You need your rectangles to be infinitely thin so that you have an infinite number of rectangles. Okay? An infinite number of rectangles means they're infinitely thin. When we're talking about something approaching infinity, I bet you we're on to a limit. Okay, so that's in fact what it is. It's a limit. So now we're going to switch back and rewrite these with limits. Okay, so now we're going to start generalizing with n rectangles instead of one rectangle, two rectangles, etc. So I'm going to zoom in on this up first. Okay, so here's the function we're trying to get, and I changed the limits of integration to 20 to 30, but we're still dealing with f at x equals x plus 3. So I want to get the area under that curve. Now, if I, for example, did have just one rectangle, and it was a right-sided rectangle, that's what the rectangle would look like, right? And so that would introduce this overestimate in area here, right? So what if I got rid of that? Okay, what if I got rid of that and I did two rectangles? So you see the error now would be significantly less, right? And then I might go to, oh, I don't know, what if I went to 4 rectangles? Okay, so then it'd be there, 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 and I'd have much less. And then I might go to 8 rectangles, right? And then I might go to 16, 24, etc. And as I increase the number of rectangles, n, that error eventually disappears if I can get an infinite number of rectangles, which means that delta x becomes dx, right? Pretty cool, eh? So a rectangle has width delta x if it's a quantifiable number. But as that rectangle becomes infinitely thin, that delta x just becomes dx, right? It's dx wide, and that's why the integral has dx in it, right? So it has a height f at x and a strip width of dx. If you sum all of those, that infinite number of rectangles, the area of those, you're going to get the overall area under the curve. So let's look at this. So remember that we set delta x to be b minus a over n. So in this case, that would be 30 minus 20 over n. Delta x is 10 over n. So that's your first thing that you do every time you're doing a question like this. If you're asked to write a Riemann sum, you do delta x. The second thing you're going to have to figure out is a formula for k, or for xk. So what does xk mean? It's just the x value of each rectangle, the first rectangle, the second rectangle, the third rectangle, right? So all the way up to the kth rectangle. So we can do this pretty easily. So the a value we're starting at is 20. So we're starting at 20, and we go 1 delta x to the right, okay, because it's a right Riemann sum. Right, this is your a value, that's the left side. Okay, that's the left side of the rectangle. To get the right side of the rectangle, I go 1 delta x to the right. So then for the second rectangle, I'm going to have to go 20 plus now 2 delta x's to the right, and so on. Well, that 1 is just your k value. That 2 is just your k value. So what's the formula? 20 plus k times 10 over n. What is that in general? A plus this 10 over n is b minus a over n, all multiplied by k. Okay, that's your x value in general. So then what we see here is this general formula. F at x dx is the same thing as f at xk times delta x, right? This is the height at the right side. This is the width of the rectangle. So that gives you the area of each rectangle, the first rectangle, the second rectangle, the third. Why do we introduce that limit as n approaches infinity? Because we want to get an infinite number of those rectangles. An infinite number, so they're infinitely thin, so there's no error. Okay, there's no error. So how would we write this then? Well, we've already figured out that this right here is xk, 20 plus 10k over n. That's xk, and the formula is y equals x plus 3, right? So then I've got to add a 3 on the end, and then it's delta xy, which we figured out to be 10 over n. And that, folks, is the Riemann sum limit notation for the exact value of the area under that line between 10 and 20. Okay, so there are 3 steps to this. Same 3 steps every single time. The first step, get delta x in terms of n. The second step, get an equation for xk, the x value where you're determining the y value. The third step is just to do the y value times by delta x, okay, with all this notation, which doesn't change. By the way, if you want to do a left-sided, all you do is let k equal 0. Okay, that will give you a left-sided. Okay, a left-sided would give you, you just put k to equal 0. Right, but I want to tell you why this is not very significant. Once you get into an infinite number of rectangles, whether you do a left or a right-sided interval, it doesn't matter. Because if you've got an infinite number of rectangles, the area is going to be perfect anyway. Okay, so that's why the right-sided interval is a little bit easier to develop, and that's why there's the emphasis on the right-sided interval with an infinite number of rectangles. Okay, so let's do just one more example here. So we're going to do this integral written as a Riemann sum. X squared from 7 to 9. Remember, the first thing is always get delta x. That's what delta x equals. Okay, b minus a over n, 2 over n. The second thing is we need to get xk. There's our xk right there. So we know that xk is, it starts at 7, right? The x value starts at 7, and then, so the general formula for this is a plus b minus a over n times by k, right? Times by k. And what is that? This is delta x, right? So we just keep advancing to the right by delta x. Advance to the right by delta x, measure the area. Advance to the right by x, measure the area. Advance to the right by delta x, measure the area. So there's your a value. 2 over n is delta x, and that's for the first rectangle. Okay, so then we have to go to the right twice from 7 to get the area of the second rectangle. Well, the x value of the second rectangle, and so on. What does that simplify to? 7 plus 2 over n times k. So that's part 2, getting xk. Part 3 is developing the height. Okay, the height. So I always do it in 2 parts. I write f at x first, which is the original function that's given. Then I write f at xk. Well, what's f at xk? That's the height, the y value, for each rectangle. Okay, for each rectangle. So we know that it's, this right here represents xk. So it's xk squared. So f at x is xk squared. And xk squared is 7 plus 2k over n squared. Finally, what I do is I put it into a formula. Okay, put it into a formula. And so I need this limit as n approaches infinity, because I want there to be an infinite number of rectangles. F at xk is the height of each rectangle. Delta x is the width of each rectangle. Our formula is x squared. There's xk, and I need to square it. And then there's delta x, b minus a over n. Okay, folks? So that's how you go about writing a Riemann sum. So, folks, let's take look at one example of going in reverse. Okay, going in reverse. And there's sometimes is one of these on the AP exam, one question like this, in the multiple choice section. So let's look at this and analyze it. So this is our general formula right down here. Okay, our general formula is here for the integral of a to b f at x dx. And then what we've done is generalized, like this f at xk is this, that's xk, and this right here is delta x. So we've got two things being multiplied together. So if we look, I've got that and that. And we want to figure out what integral does that represent. Well, I know it's got a square root in it. I know it's got a square in it. So if I look at the innermost part of this, that should mean my xk. So in other words, this right here, that part there, I'll highlight it in yellow. That part there has got to be my xk. That's my xk. So the first value in that is always a. So in this case, a equals -1. Okay. What is this part here? 4i over n. Okay, 4i over n. Oh, in this case, they've used xi in this case. It doesn't matter. You have to be able to use both I and k for that value. So then that means that 4i over n has to equal b minus a over n multiplied by I. Okay, so that means if you look at this, right, that means that b minus a equals 4. b minus a equals 4. We know that a is -1. b minus -1 equals 4. Wow. So b plus 1 equals 4. b equals 3. Okay, b equals 3. So that means that we're going to do an integral from -1 to 3. Okay, and then what else do I have here? Well, really, so they've reversed this, right? So that 4 over n's out front there, it can be also at the back 4 over n, and that has to be delta x, b minus a over n. Does that work? What's b minus a? Is 3 minus -1, which is 4. That works. Okay, so I've got square root, so let's write it down here. It's the integral from a to b, and a to b we said is -1 to 3, right? -1 to 3, which is where that 4 comes from. And like -1 to 3 is 4 units. Then it's going to be square root. I'll circle in green the x value. There's the x value right there. So it's going to be 3x squared plus 2 dx. Okay, and that's about as hard of a question as you could possibly get. Okay, so I've got another screencast from someone else that I'm going to post with this, and then a handout with questions. Again, this is something that there are very, very, very few multiple choice questions each year, usually one. So hopefully that's a long screencast, but hopefully it helped a bit.